So welcome to the operations research course. So in this lecture, we'll continue with the simulation lecture. So in our last lecture on simulation, we had introduced the concept of simulation, the types of simulation models. We have looked at the simulation process and we have used the multi-Carlo sampling process to undertake a stochastic simulation of activity. And we have looked at how a queuing system can also be built through a simulation system. So in this lecture, we want to look at generation of random variates. So we'll look at generation of discrete random variate, then we'll look at generation of probability density functions, using that to generate random variate. That is, you generating random variate for discrete and also generating random variate for continuous variables. Then we shall look at using Excel to generate some of the random variables, whether it's based on a uniform distribution or a normal distribution or Poisson. And finally, we'll look at the determination of the distribution of various random variables. And if we have some time, we'll look at the test of goodness of faith, analysis of simulation output, and simulation languages which are used to model some of our simulation models. So let's go straight to the generation of random variables. I would move to my whiteboard here so that we can go straight to some of the applications. All right. Okay, so in the previous lecture, we had assumed existing random numbers, however, in a typical environment, we are faced with generating our own random numbers. Most of the random variables are actually statistically variate, from a certain distribution. So, for instance, the distribution will be the one that adequately represents the physical process involved at that point in the experiment. For instance, when you are collecting the data from the field, so you have a set of data that has been collected, and then you generate statistical random variables from the data. So we look at the distribution of the data which has been collected, then use that to generate the random variates, right? Or the random numbers, right? So that's how it's actually done. So the general process for generating the random variates or the random numbers from a particular distribution will actually, follow some steps. For instance, you have to generate a random number from the uniform distribution. Let's say that the data you have, follows the uniform distribution. Then it means that you have to generate random numbers from the uniform distribution. Then you perform some mathematical transformation of the uniform random number or the numbers which produces a random variance from the desired distribution. Then you use the transform variance in the experiments as desired, like as we've computed in the previous examples, right? So usually when you are dealing with uniform random numbers, so uniform random numbers, when you are dealing with them, you actually generate the numbers from the uniform distribution over a range of 0 and 1. If you are also generating, let's say, random numbers from normal distribution, you still generate it, based on 0 and 1, right? So the most common method of generating random numbers on a digital computer is by algorithmic recursive equations for generating the pseudo random numbers. We shall open Excel and look at some of them, right? Okay, so usually it is important to know that the properties of a uniformly distributed numbers, include the number generator should, as nearly as possible, be uniformly distributed. The generator should be very fast, that is if you are using a computing power, it should be very fast. The generator should have a long period. Sometimes you generate some random numbers and they tend to repeat itself. You don't want that kind of random numbers. The generator should be able to produce streams of numbers depending on where it starts from. So there should be some variations in the numbers which are being generated. Now the generation method which should not degenerate to repeatedly produce a constant value. So sometimes you generate a value or you generate some numbers and you end up with, let's say, constant values, and then it moves throughout. That's not the best. Then a generator should not produce a zero. It's not produce a zero. So we shall look at three main methods of generating before we go to our Excel. So the first one is the mid square. The first one is the mid square technique. All right, so the mid square technique actually employs what we call a seed value. So the seed value is usually the first number in the series or the first random number in the series. So to generate the random numbers, you need to start with an initial first number, right? So the seed number is actually squared and the selected middle digits are used as the random number. So for instance, let's take an example, So let's say that our initial seed value, which is also a random number, right? Let's say random number naught is 1345. So the mixed square technique says that you should square this. The first random number will be 1345 square, right? And 1345 square is 1809025. So what the mean square does is that you take, because the seed value is 4 in this case, 4 digits in this case. So you ensure that all your other values are 4. So what you do is that I take this 4 and I can put 0 here, right? So it means that my next random number is actually 8090. Sorry, so the next random number is based on the square of the just generated random number. So the square of the just generated random number is 65448100. So when you take the 4, right, you're going to get 4481. So that's the random number. So the third random number will be 4481 square. So 4481 square is actually 2079361. So if I'm to look at that, so I have 7930793, etc. So this is so random 4 will be 793 square, right? So 793 square is 62884 9. So 62884 9. If we are to look at the 4 digits, so then that will be 2884, etc. So this is how we generate it, and you can use a computer to do that. So we will actually do that in Excel, but let's look at the second method. So the second method that we will consider is the made product method. Is the made product method. All right. So the made product method, what it does is it's based on the next random number is actually a constant, and the current random number, right, or the current seed value. So if R naught, which is Rn, is the seed value or the initial random number that we are being used or that we are using, right, then A is our constant, K is the constant, then the next Rn plus 1 is actually the middle digits of the product, KRN, right? So if we are to take an example, and we say the seed value, which is Rn, is 1565, and K is 4213. Then R1 is actually KRN, which is 4213 by 1565. So 42131565 is 659345. So if we are to take the middle, remember the seed value has got 4 digits, right? So if all is 4 digits, you have to ensure that your random number is also 4 digits, right? So we have this, we can put 0 here, and we'll have this, and we'll be able to say that the first random number is 5933. So the second, which is KRN plus 1, right, is actually the K is constant, so it's still 4213, but the Rn plus 1 will then be the 5933, the one which was just computed. So this is going to give us 5933 by 4213. I'm going to have 24,995,729. So if we are to take the 2 and take the 2, then we are going to have 9957, right? So that's the random number, 9957. So the next random number, R3, is actually KRN plus 1 plus 1, right? And that will be all. Let's do this one. It's KR2 plus Well, or just R2. R2. So now we 4213. And what is R2? 9957. So 9957 by 4213. And that is 41948841. And this will be 9488. All right. So this is how the made products method. Very simple and very straightforward. All right. So the third method is the multiplicative. The multiplicative congruential method. So this method is known to be the most widely used method for generating random numbers, right? So the main reason is that they generate random numbers that are more uniformly distributed and generally require less computer time and cost. The sequence of random numbers is also reproducible, and the period can be made to be very long before cycling. So it's actually given by the next random number is actually a constant times the random number mode m. So the m is actually the first. So the m is the modular. So you have this expression, right? So let's take an example, right? Let's take an example. So we know that the A is a constant multiplier, the Rn is a seed, and the M is the modular. So let's assume that we have an example where the seed, remember the seed is the R1, the first random number. So the seed is 29, A is 17, and modular is 100. So the R2, second random number, is actually A R1. So what is A? A is 17 by R1, which is 29, mod 17. And this will be 493 mod 17. And the answer is 93. All right, the answer is 93. So if it's 93, you can later divide by 100 and get your get a random number between 0 and 1. Right. So the next random number will be the 17, which is the constant, times the just computed random number and mode. No, sorry. So the mode is 100. The mode is 100. Yeah, the mode is 100. So this will be 1581 mode 100, and that will be 81, and we can see it's around that, right? So can determine the fourth one and say that will be 17 by 81 mode 100. So 17 by 81 is 1377 mod 100, and that is 77, which can be 0.77. So usually the larger the mode number, the more continuous, or the larger the number of random numbers that can be computed, right? So it has been found out that to generate about 2 billion numbers, per cycle of a given seed, the the seed value should range between 1 and about 2 raised to the power 31, you know. Yeah, and this principle has been used in the SEMA language, which is used in the arena simulation software, right? Great, and the multiplier is 16807. Is basically used. All right, so we shall go to our Excel sheets and generate some of the use some distributions to generate some random numbers. Let's go to Excel sheets. Okay, so we have a typical Excel sheet here. If you can actually see my screen. So for a typical Excel sheet, let me try and see if I'm sharing my screen here. I'm doing it. So a typical Excel sheet, so you go to data analysis, data analysis, and you should have it here. If you don't see your data analysis here, you have to go to, I think, file. Yeah, and go to file and add it as an add-in. I don't think you have to use add-in. File and so file and options, and we should see add-in here. So you can then go to any inactive application here and add them, or just come to it, yeah. So if you don't see them here, yeah, you can add the add-ins here, the Excel add-in here. All right, so I already have it here. So I open that and I see random numbers here. So random number generation. So I look at the generation of these numbers. So let's say that we want to use uniform distribution. Okay, so you want to use uniform distribution, right? So we know uniform distribution to be made up of a mean, which is actually the two extreme ends of the distribution. Two extreme ends of the distribution. And we have a standard deviation given by the square root of the two extreme ends raised to the power 2 divided by 12. So if we have that, then we want to generate, let's say, 2 rows of random numbers and 100. So what are the two extreme values? So assuming one is 20 and the other is, let's see, 80, and assuming we have a seed value of 1456, and I want to output my variables, or the random variables in column A. So when I click on OK, then it's going to generate the random variables for me. And that's it. Very easy, very simple, right? So assuming, I'm not going to delete that. So assuming I want to determine another one using the normal distribution. And the mean of my data I've found out to be around 65. And there's a standard deviation of, let's say, 12. Let's still use the seed 4056. But now let's pick this column T. So I run it and I'm able to get another set of random numbers, right? So let's try the third one. Maybe could be the final one. So we have the Poisson distribution, and with the Poisson distribution, it has the lambda, which represents the mean, right? So we have the lambda, which represents the mean. So let's say that the mean number of occurrence is 25. Let's use the same seed. Now we want it, the results will appear in G. So when I run them, I have these values as the random variables. So basically, that's it. And you can then use these values as your random numbers. So random numbers in the Monte Carlo simulation. All right, so I think we can end the generation here. Yeah. And okay, let's look at the generating random variable for continuous variables, right? So usually for what we've done so far is for discrete variables, right? It's for discrete variables where we did the daily demand, we did the shovel truck haulage examples, right? But what if you are generating for a distribution, right? You are generating random numbers for a particular distribution, right? So several techniques are available. So we have the inverse, transformation method, right? We have the rejection method. We have the composition method, and we'll also have the mathematical derivative method, and finally we have the approximation method. All right, so the use of a particular method will depend on the type of distribution that is involved in the simulation experiment. As usual, as I said, you always pick the data and you look at the distribution of the data, then you can, based on a distribution, you can use that to develop the random numbers. So the use of the inverse translation method will be used in this case. So we can go back to our whiteboard and take an example using the inverse transformation method. All right. Okay, so before we do that, let's go back to the Excel and let's replicate this multiplicative congruential method in the Excel environments. I think we'll be able to do that, before we look at the inverse transformation method. So let me bring back the Excel sheet. All right. So the inverse multiplicative. So assuming all these are off, right? So the inverse multiplicative, we actually discovered, or we found out that it's actually based on this formula. The next random number is actually a constant, times the current random number, and mode M. So we took this example and said that assuming we have a seed of 29, we have a constant of 17, and we have mode 100, we can generate this. So what we want to do here is, let's say I want to have seed value, right? So the seed value is my initial Rn, which is 29. My A constant is 17, and my modular is 100. So my next, let's see, the next random number is actually mode. So constant is 17 times the Rn, which is the C value, is 29. And the divisor, which is the modular, is 100. So when I run this, sorry, I don't need to type them. I have to pick this, make it a constant. Yeah, A is constant. I have to pick this value, and then I have to pick the divisor, which is also a constant. All right, so that's 29. Sorry, 93. So R3 will be, let's just drag here, but now instead of the E8, E8 has to be 93. So we still maintain the constant A times Rn. Now Rn is 93, and the modular or the divisor is still 100. So that's that. So we can drag this down. All right. Yeah, so we can drag this down to the next 100. So that's it. Very easy and very straightforward. All right, so let's go back to the random number for a typical distribution. All right. So now based on the inverse transformation method in determining random numbers for a typical distribution function, for a typical distribution function. So assuming that we have the typical distribution function, the probability distribution for a random variable x, right, which represent in the arrival time of a typical machine or dump truck, right, is defined by fx, which is x over 8, for a region of x from 0 to 4. Right, so we can actually plot these values. Yeah, can plot this value and have fx with x, so you can have fx with x. For instance, if fx, x is equal to 0, So then we have x is equal to 0. So we have that value 0 if 1 on 8, fx 2 on 8, that is 1 on 4. So fx 3 on 8, then fx 4 on 8, which is half. So we can plot this distribution as 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. 0.5, 0.6. So we have that. We can also have 1, 2, 3, 4. So we plot fx0 for 0, which is that. Then fx1 on 8 and 1. So we have 1 on 8 somewhere. 0.15 is here, so around 0.1. Then we have 2, 1 on 4. So 1 on 4 is 0.25, 25, 25. Somewhere there. Then 3 divided by 8.37, somewhere here. Then 4 half 0.5. So that is that function. Yeah. So x and fx. All right. So this is the probability of the occurrence of the x, right? So usually for us to get a distribution, right? So we need to determine the cumulative distribution function. So it's basically the area under the curve, right? So it's usually the area within the area, and therefore we need to mathematically determine the cumulative distribution of this area, and it will surely be the integral of the density function, over the limit from 0 to x, from 0 to x. So it means that the cumulative distribution, right, will be an integral, for, let's say, t, t. So if we are to break this down, we are going to have this from 0 to x, and this will be the same as that. So this is our cumulative distribution function. All right. Again, this is true for x less than or equal to 4 and greater than or equal to 0. So we can then plot a parabolic graph for this distribution, so that we can now use that to determine the random number. Right, can now use that to determine the random number. So we know that the cumulative distribution is actually the random number, which is giving us that's on 16. So if we are to go through this, x2 is actually 16r. So x is square root of 16r, which is actually 4 square root of r. So it means that x, which is actually the inverse of this function, is the 4 square root of the r, right? So it means that we can then, it means that we can then determine the function. Okay, yeah, so we didn't, yeah, we could have plot, so we can plot the distribution. We can plot the distribution fx is equal to s squared over 16 for 0 less than equal to x equal to 4, and say that if x is equal to 1, then it means that fx for 1 is 1 on 16. If x, okay, let's do for 0 first. 0. Then let's do for 1. That will be 16. Then for 2 square on 16. So that is 4. That is 1 on 4. Then f3, 3 square on 16. So that is 9 on 16. Then F4 is 4 square on 16. That is 1. So we are going to plot 0, 1, that, and that. So we can easily have this parabolic. Our fx, the cumulative distribution, our x. So let's say 1 is here, 2, 3, 4. Then 1, 2, 3, 4, 5. Okay, so 0.1, 2, 4, 6, 8, 1, 0. So the first value is that. Then we have 1 and 1 on 4. 0.3, 0.25, somewhere here. 2, no, it's 1 on 16. 1 on 16 is somewhere here. Then 2, yeah. Then 3 is 9 on 16, which is around 0.5. In the middle, 0.5, 0.6 there, but then we have 4 and 1. Yeah, so this is a parabolic curve, something like that. All right, so then we can use this function, which we can just select from the graph, or we'll go back to our x is 4r. So we can have our first seed, and say that if a random number is 0.5, 0.25, right, is generated from the simulation process, right, based on the Monte Carlo sampling, then we can say that then the corresponding distribution or continuous variable is 4. Right, so assuming we pick this example, then it means that the answer is going to be around 2, right? Around 2. So assuming we want to pick that 1.3.5, let's use this. Yeah, not drawn to scale. So not drawn to scale, but at least we see it matching somewhere, you know. So that's how a random variate for a typical distribution can also be generated, you know, which is different from the discrete form. So I think we'll end this lecture here on the generation of random numbers. I'm hoping that you'll be able to apply this to a real world scenario or issues so that you can be able to stochastically sample to say stochastically, you'll be able to generate some random numbers and be able to assess the variability within a system that you are working or you are finding the performance or evaluating. So on this note, we'll end the simulation lecture here, and we hope to see you again in our next lecture. Have a good day. Bye-bye.